Okay, so let's have a look at discrete logarithms. And we'll try and understand how they're used inside cryptography. So it was John Napier who actually defined the rules of logarithms. So for that, he said that g to the power of x times g to the power of y is equal to g to the power of xy. And g to the power of x to the power of y is equal, g plus x plus y, and this is g to the power of xy. Okay, so g to the power of x times g to the power of y gives us g to the power of x plus y. G to the power of x to the power of y gives us g to the power of xy. So that's our basic logarithms. Discrete logarithms, though, brings in a mod of a prime number, and it becomes discrete. And the great advantage of using the mod p is that we can still do our computation and it will still work out. So for example, if we take g to the power of x mod p times g to the power of y mod p, that will equal g to the power of x plus y mod p. So how does this actually work out? Well, basically what happens is that we are constraining it inside values between 0 and p minus 1. So g to the power of x for every value between 0 and p should give us a different value when we take a mod p operation. And the values that we should get will range from 0 to p minus 1. And we've got to be sure that we select the g value so that every value of x between 0 and p minus 1 will result, when we take mod p, in a range of outputs that will range from 0 to p minus 1, and we'll get different values for each of these. It then will wrap round, and when x is larger than p minus 1, then we'll still get the values constrained between 0 and p minus 1. Okay, so if we were to draw this as a little set, we'd actually find the values of x will map to g to the power of x mod p. So there would be a direct relationship from the values here into the values here between 0 and p minus 1, and every value will be included in this set here between 0 and p minus 1. So that's the basics of discrete logs, and the magic of it is the mod of the prime number. Remember, the mod is the remainder after we do an integer divide by p. Okay, so let's look at the three main areas that we apply discrete logarithms into cryptography. And the first one is in key exchange. And with this, we have the Diffie-Hellman method, created by Whitfield Diffie and Marty Hellman around 1977. And they proposed that it would be possible to have a key exchange method between Bob and Alice, and where when we exchange values, then Bob and Alice will end up with the same shared secret value. Let's call that K, or for K for an encryption key. So the way this is conducted is that we initially start off, Bob generates a random value, and Alice also has a random value. The first thing they do though is they agree on a value of G. Remember, we've got to pick G correctly, and a prime number P. So they both agree on that, and then the value of B will be between 0 and P minus 1, and the value of A will be between 0 and P minus 1, and will hopefully be random. Bob now computes his public value. This is the value that he's going to transmit to Alice. So Bob is sending over B, and Alice is sending over A. So Bob computes G to the power of B mod P, and Alice computes G to the power of A mod P. So they don't give away their A and the B, the small a and the small b value. Then they send these values over, and then to work out K, Bob takes B and then takes A that's received here, and then raises it to the power of B mod P. Over here, Alice does the same thing, takes Bob's value, raises it to the power of A, then mod P. And just like what we had here, then K is equal to G to the power of A to the power of B mod P, and K is equal to G to the power of B to the power of A mod P. And then in the end, they'll both get a shared key of this. And this means that they both end up with the same shared key at the end of it. And hopefully if Eve is observing the values of A and B here, then she won't be able to determine the actual result. The size of the prime number is very important for us and will give us the basic security of the system. And P typically has to be greater than 1024 bits, probably even greater than that, 2048 or even up to 4096. The Diffie-Hellman method isn't used that much these days because of the large size of the prime number, but it's certainly a valid method when we look at our discrete logs. So the next method we'll look at is the ElGamal encryption method. And this was created by ElGamal. And what we have is that, again, we have Bob and Alice. And they have key pairs. So let's say Alice has a public key, and she also has a private key. So this is our public, and this is our private key here. What we're going to do is that Bob has some data. He encrypts the data with Alice's public key, sends it over, and then Alice will decrypt with her private key. In this case, we have encryption. So it's rather like symmetric key encryption, but we're using this key pair. The public key is made public to anyone who wants to communicate with Alice. We need to make sure that Bob gets that in a trustworthy way, but let's assume that can happen. Once we have Alice's public key, then Bob sends it over. She decrypts with her private key. Okay, so let's see if we can make this work for our encryption. So let's say that we're looking at Alice creating her key pair. Initially, she defines X as her private key. Again, we define the prime number that we're going to use for that, and we also select a G value or a generator value as we did here. So Alice generates a random number between 0 and p minus 1. She then computes her public key, or part of her public key, which will be g to the power of x mod p. And that's it. So Alice's public key becomes y, g, and p. So she will send that over to Bob for Bob to encrypt data for her. Okay, so let's say the data is called m. It's an integer value. We convert our strings into integer values. So we'll encrypt this and send it over to Alice, and Alice will use her private key here to be able to decrypt it. Okay, so Bob then computes two values. And this value here, k, is a random nonce. So every time that Bob encrypts for Alice, he generates a random value. We don't need it after this, but it makes sure that the encryption process is randomized for its output. So he will take g to the power of k, the random value, somewhere between 0 and p minus 1, and then we'll take Alice's public key, y, raise it to the power of k, and then multiply by m. Okay. So then Bob sends the values of a and b over as encrypted values to Alice. Now she needs to use her private key to be able to recover the message, which is obviously m here. So the way that she does this is she takes b divided by a, and a is raised to the power of x, her private key, and takes mod p for that one. And that should give us back the message. So how does that actually work? Well, if we take that, then the value of b is y to the power of k times the message divided by a. So a is g to the power of k to the power of x. Okay, so y is g to the power of x to the power of k times m divided by k x. And look here, we've got kx there. So g to the power of x k m divided by g to the power of x k is equal to m. So that Alice will be able to recover the message. So Alice has used her private key to be able to decrypt. Bob used her public key to be able to create the encryption, and then this is then computed. Again, we're looking at prime numbers greater than 1024 bits to be able to keep it secure. Okay, so this is for encryption. This is for key exchange. Now let's look at signing for the message. So our third method looks at digital signing. And for this, we can prove the ownership of a private key. So our third method is digital signature algorithm, or DSA. And this was created by David Kravitz and was patented, but was assigned to the US government. And DSA was one of the first signature methods after the RSA signature method. It has since been developed into ECDSA, and in most cases it's ECDSA that we use these days because it uses elliptic curve cryptography, but it's still based on the basic methodology of DSA. Okay, so let's have a look at how this actually works. So in this case, we have Bob and we have Alice. And the main difference that we have now is that Bob is going to sign a message to Alice. So here's the message that we have. Let's call it M again. And Bob will have his public key and his private key. What happens in this case is that Bob will sign the message to create a hash, or to create a signature of the message. And he'll sign that with his private key. That is then sent over to Alice, and then she will use his public key to verify the signature so that she knows that it was Bob who signed with his private key. This is the concept of a digital signature. Okay, so let's see if we can get this to work out. As before, as we have here, then Bob creates his private key as X. Again, we agree on a prime number and we agree on a generator value, the G and the P here. Okay. So the value of X will be somewhere between 0 and P minus 1, and will hopefully be a random value. Next, Bob computes his public key, and as we've seen, his public key is just G to the power of X mod P. And in this case, P is quite large, probably 1024 bits and above. So it's quite a big value that we have here. We then compute two values of R and S. So the signature itself is R and an S value. The R value is equal to G to the power of X, where Bob creates a random nonce. So what we have is that our signature, we're going to use a K value or a random nonce into the signature, and then takes the mod of P. This value will be rather large, so we bring in another prime number called Q, which is smaller than P. So that constrains our values of R much more than having this large value here. So Q shrinks R into a usable range. We then calculate the value of S, and S is equal to the inverse of K using a mod operation, and then we take the hash of the message plus XR, and we take that for mod Q. So we take the message and we take the hash of the message into our signature, and also we bring in our private key. This will produce the value of R and S here for our signature. Okay, so notice here the private key is used there to create the signature. This is the random nonce that we're creating. This is the hash of the message. So the hashes are typically SHA-1, SHA-256, and so on. Okay, so that has created our signature value, and the message goes over. Bob will send the value of RS over to Alice, and now she has to work out that if Bob has actually signed it. First value that we compute is that we take the inverse of S mod Q. This is a fairly standard operation that we have. It's the inverse mod of S, the inverse of S mod Q, and we can get libraries to do that for us. But it's basically the inverse of S mod Q. We then compute two values. We take our own hash of the message, and then we take W, and that's mod Q. Remember, mod Q constrains the values of R and S. For U2, we take R times W, and again we take mod of Q. Finally, we take V, which is G to the power of U1, G to the power of U2. We take mod P and mod Q. Now, if V is equal to R, then the signature checks. So let's see how that actually works. So V is equal to, here we are, G, and we have, we'll just call it H, it's the hash of the message, times W, multiplied by G, and then that should be RW here. I'll leave off the mod part here just to show the proof, but obviously we're taking the mod operations here to make it work. So that's G. At which the value that we have here, G to the power of X. This should be Y. Just let me use that there. This value should be Y. Y. Okay, so that becomes HW, and that will become G to the power of X, as we have here, to the power of XW. So if we compute that, then that is HW plus XRW. And we can then define that we have the value of S. S will equal W will equal the inverse of S. So that will be H plus and H plus XR all divided by S here, because we're taking W out and it becomes the inverse there. So if we now look at this part in here, okay, so we have G to the H plus XR divided by K to the minus 1 H plus XR, and now we should see that that cancels with that. The inverse K will come up back up the top, so we end up with that, and that is what we've got here, because that's equal to R here. Okay, so that's just made a little slip there, but that's how we prove our DSA method. Okay, so what we've covered really is discrete logarithms and how they're actually created. Then we look at the three main places that we can use discrete logarithms: for key exchange, for encryption with ElGamal, and then with a digital signature. As I said, we now use ECDSA here. For this, we typically use ECDH, so there's the DH. So rather than using discrete logs, we use elliptic curve. And for ElGamal, well, we don't really use it that much. We typically will use RSA for our encryption methods. But the theory all works out. Okay, thank you.